So now it should work, and we will start sharing. And first of all, I will move to JASP, and we will be, as the first step, briefly reviewing topics that were covered last time. So I will only switch off my camera briefly. Here it is. So before we start, once again, this is the data file about description of approximately 260 flats from the Czech Republic. And for the first insight, the most important variables are prices and sizes of the flat. So previously, and we would once again repeat these steps, we were correlating prices and sizes. According to our expectation, prices and sizes are correlated positively. This correlation is quite a big one. And I hope that maybe you remember that for analytical purposes, we extracted one flat which was quite extraordinary, as its price was approximately 3 million, but its size was extremely huge. It was more than 430 square meters. So that's only a brief recap, but now we will compute correlation analysis to repeat basic results from previous lecture. So if I would like to compute correlation, so I would go into regression, correlation, and now I'm switching into the window with input of JASP. So if I would like to correlate sizes and prices, and if I would like to make a chart for which size would be on horizontal axis or x-axis and price on y or vertical axis, the best solution is to include as the first size only in two variables, and the second variable that should be defined is price. First of all, JASP will compute correlation coefficient, and if we are computing with original data, so no exclusion of an extra big flat, so this correlation would be 0.649. And last time we were also using description in chart, so I would ask for plots, scatter plot, densities for variables, statistics, and confidence intervals. And if you wait for a minute, JASP will prepare for you graphical output. And by this graphical output, we will very simply recognize that this huge flat should be excluded from my data analysis. So one golden rule for data analysis: before you start analyze data, every time try to visualize your data. It means try to see some pictures of your data, and by these pictures you can recognize some strange patterns. So here it is. This is prices and sizes. No, yeah, it seems, and this is one very extraordinary flat. No, it is just reversed once again. So excuse me, I will reverse it once again in the output. So I don't know why is it once again reversed. So price size, I hope it will help to our graphical picture. So once again, now it seems it's correct. So these are prices and these are sizes. And you can see that this big flat may be quite extraordinary, shifted this line, which we will call in few minutes regression line, as it is influencing quite a lot the shape of this regression line. So we will discuss about this point next time as about influential point, and we should exclude this point from my data analysis. So it is probable that this regression line without this point would be something like this. And it is also expected that correlation coefficient will be slightly shifted up. It means that the real value is maybe bigger than 0.649. So once again, repetition, how it works in JASP. So if you like to exclude some values, you would click here on the left upper corner of your data matrix, and you can filter some data. And for us, it is enough to say that if the price, double clicking on the variable, once again, only double clicking. So, price is lower than 200 square meters. So then we will omit the biggest flat in my data. The last step is you need to click into apply pass-through filter. And now if we close this filtering, you should see at the beginning of the data that one flat is omitted from my analysis. So I hope it works. And the JASP should recompute our picture in a few minutes. Now it is not prepared, so maybe once again to check whether it works. So now it seems improbable. Not price, sorry for that. I might mistake, but sizes should be below 200 square meters. So I will cancel it. So size is less than 200 meters. Okay, and it works. So JASP is now recomputing as it should be. And if we wait some time, so we can see that correlation is currently 0.685, and this strange point is not included in my picture. And now it seems that this line is describing quite well the set of my data. So it means these individual combinations of sizes and prices of flats. So this is the first introduction. And we know that this is quite correct approach, that we excluded quite strange point with the big size and quite extraordinary combination of size and price. So now we will briefly go through the presentation. So before we start the discussion and computation of regression analysis, we should discuss about some basic terms. So usually we differentiate between so-called simple and multiple regression. Simple regression means that there is only one variable which is called dependent and one variable which is called independent. So we have only two variables in one data analysis. This is a very simple case, usually quite unreal case for social sciences, but we will start the introduction of regression by this simple regression example. The next step, I guess that maybe next lecture, is that we will move to the real multiple regression example. So it means there are more than two variables at once. There is one dependent variable and more than one independent variables. So if we call variables dependent and independent, there are also two alternatives to these expressions. Instead of dependent, sometimes we discuss about outcome, and sometimes we also discuss about explained variable. If we switch into our case, so according to my opinion, we would try to explain prices, so it means vertical axis, by sizes of flats. As it seems, at least for me, realistic, that sizes are influencing prices. So I would call prices as dependent variable, outcome or explained variable, and sizes on x-axis as independent variable, explanatory variable, or sometimes we also use predictor. So if I go back to my presentation, so there are usually pairs. So if I discuss about dependent, I discuss about independent variable. So these two terms are paired. If I discuss about outcome, I discuss about predictor. And if I discuss about explained variable, I am discussing also about explanatory variables. So these two are every time related. And for the easiest regression model we will be treating for the first lectures, that is called linear regression, it is expected that your dependent variable would be long scale. So we usually call these variables as cardinal, continuous, quantitative, and maybe also other terms can be found. So, for example, for us, we would be modeling prices of the flat, and you can see this quite long scale starting at approximately 200,000 up to 3 million. So that's cardinal variable, and this assumption is followed in my data. For independent variables, so it means here it is, for example, size of the flat, but in general for independent variables, they should be also cardinal or continuous, or the another option is that directly in a regression model, I can include binary variable. It means variable with only two options. But through set of binary variables, and we will discuss about it later, it is also possible to include into regression analysis a variable which was originally nominal or ordinal with more than two categories. So we will discuss this approach as a dummy variables approach. So that's only a brief introduction of basic terms and basic assumptions of linear regression analysis. And the main goal for regression is to find some, for linear regression, line that is describing the pattern in my data. For example, here you can see the pattern is that if the size of the flat is increasing, the prices of the flat are also increasing, and this pattern is described by this line, and also these blue lines seems to me that these are confidence interval for the estimation.
I'm sorry, can I ask, please?
Yeah, of course.
I don't have the latest version of the JASP, so I don't see the regression lines in my outputs.
Yeah, but that's not a problem. We
Okay.
will not discuss it in detail, but only if you have this version, so you should know that this is confidence interval.
Okay, thank you.
And of course, feel free to download the newest version of JASP as well.
Well, I cannot because of my operating system.
Okay. So sorry for that, but we will not use it for some special tasks. So only you should know that for newer versions in JASP, it is included, and it is confidence interval of estimation. Okay, thanks for your question. So here it is, how it works. And now we would go into detail, and we would learn how JASP or another analytical software will find equation. So it means some formula for this line. We will also discuss that every line has two parameters, one which would be called as a constant or intercept, and it is only intersection of this line and this vertical axis. So here would be something what we would call as intercept. And also every line has its slope. So it means whether it is increasing or decreasing or non-decreasing, non-increasing line. So it is the slope. So these parameters of the line and how we can find the equation of, let's call it ideal line, and this would be our next task. So let's go back to the presentation, and main goal is to find the line. So it means explain dependent variable by independent variables. And if we would like to apply this simple linear regression model, it is expected that the relationship can be modeled by the line. So if I would like to apply linear regression, line should fit to my data. Here it seems that it works, but sometimes in real cases, and we will briefly discuss about it in next 2 weeks, this assumption is not met in your data, and that's why linear regression shouldn't be followed, and you must follow some special so-called nonlinear models. And also, if your dependent variable wouldn't be long cardinal scale, also for these cases, linear models wouldn't be accepted, and you should once again switch into nonlinear models. So these are examples of usage of so-called nonlinear models. And our main goal for this first introduction would be that I would like to recognize properties of these lines. Once again, every line has its intercept. So it means whether it is here or here or here, there is the intersection of this line and y-axis, and every line has its slope. For example, this is quite steep. I can make the line such as like this one with more slope, or with no slope at all, with negative slope. So this is the second property of the line, its slope, whether it is increasing, decreasing strictly, or whether the slope is only a small one. So let's go to some pictures and descriptions. Once again, repetition of assumptions. One cardinal dependent variable, and for simple regression, it is expected that you have one cardinal independent variable, and it is expected that your relationship follows approximately line. So it means that these points are quite close to the line, and that the pattern of the data is following the line. One more comment: if your points are quite close to the line, so it means that your model fits to your data quite well. If these points should be quite far from this line, maybe that your model would be quite poor. So for these data, you can see that these points are quite close to our regression line. So it means that this description, this model is quite good for my data. So that's only first graphical insight. And here is once again repeated golden rule of data analysis. Every time before you start regression, try to describe your data by chart. Okay. And now we will try to answer some basic questions in regression analysis. So first of all, we will discuss about algorithms. It means some mathematical procedures that can help us to find the line that is the best for my data. Next one, we will discuss about the meaning of regression equation. It means about parameters, about intercept and slope. We have covered briefly this topic previously. And then we will discuss about the quality of model, so whether my regression is good or not. And we will be discussing in some next lectures about improvements of regression model, about inclusion of other variables, etc., etc. So here is second picture of some regression line. This is a picture which is copied directly from NDField textbook. And here you can see that this picture is not so nice as is our current picture. So here the points are quite close to the line. Here points are not so close to the line. And this is the picture of advertising budget and number of record sales in thousands units. You can see still that there is some positive relationship. So it means the more you invest into the recordings, the bigger are the sales. So as this line, which is red one here, is increasing, but you can see that this portion of these points, real combinations of advertising budget and recording sales, is quite diverse in comparison with my picture. And now through the next picture, we will discuss how it works, and we will briefly also discuss about meaning of individual parameters in ordinary regression analysis. So first of all, here you can see 1, 2, 3, 4 points. So for this picture, we have only 4 points for real data. So these black points are real data. And if I would like to find relationship for these two variables by these 4 points, I can apply some techniques which is called ordinary least squares, or in shortage only OLS. For Czech students, we call it metoda nejmenších čtverců. Okay, and this ordinary least square techniques is following this quite simple logic. So you would try to find a line, here it is prepared for us, that is flowing, that has flowing property. If you take the distance from every point to this line, I mean vertical distance, so it means this distance, this one, and this one, and you take the second power, it means in graphics square from this distance, we call this distance, and we will be discussing it repeatedly, as the residual. So difference between real value and value which is expected by my model, by this regression line. So I would take residual squared, I would take these squares, the first one, second one, the third one, and the last one, and I would sum up spaces for these squares, or I would sum up squares for residuals. So this line follows the property that for this line, and only for this line, the sum of these squares is the minimum. That's why it is called least squares, as the sum for all these squares for this line is the minimum. And if you would take another line for all other lines, the sum of these squares of residuals would be higher. So this is ordinary least square techniques, how it works. And if you are preparing this line, so usually every line has its own equation. And in statistics, we usually use equations such as y, it means vertical axis, is based on something what is called intercept. Usually we use B0, and then the impact of independent variable on x-axis multiply by something what we usually call slope. So constant plus impact of slope multiplied by independent variable gives estimation on this line of dependent variable. And now we should discuss about these two parameters. So B0, as we discussed about this on JASP example, so if you take intersection of your line and y-axis, so this is the constant or intercept B0. So in other words, it is the value of dependent variable if independent variable is set at 0 value. So if I go back to my real life example, sizes of the flats and prices of the flats, can somebody try to explain what could be the interpretation of intercept here for this case of sizes versus prices of flats? What would be interpretation? Can somebody try?
Maybe if the price is 0, so the size is 0?
No. The interpretation would be, what would be the price of the flat if the size of the flat would be 0 square meters? So it means it would be no flat in reality. What would be price of such a flat? I guess you can understand that this interpretation is quite artificial. So there are no flats that are 0 square meters, at least still they are not on sale. So for most of social science examples, as 0 is usually useless, interpretation of the constant by this very simple tool is also useless. So for us, this interpretation would have no sense, but we would slightly change the scale of independent variable in a few minutes, and then we will change also this style of interpretation. But in generally, the meaning of intercept is if independent variable is set on 0, what is the value of dependent variable? So this is usually, once again, quite useless. And that's why, and it's a pity, social scientists usually omit the interpretation of intercept or constant. So we will learn how to overcome such a weakness of classical intercepts in regression analysis. The second and usually more important part of regression equation is B1. It means something that is describing the influence of independent variable on dependent variable. Once again, in our real life example, it would describe how sizes influence prices of flats. So here it is. It is called B1, usually slope, and the interpretation by the picture is quite simple. So if you add one more unit on x-axis, so increase, or sometimes of course decrease if the line would be going down. So if you increase by 1 unit independent variable, B1 says how much is increasing or decreasing your dependent variable. So 1 unit change on x, and the result slope says what would be the change on y-axis. So if I go back to this example about prices and sizes, can somebody help me to explain what would be the meaning of the slope here if sizes are independent and prices are dependent variable? Can somebody try? Okay, so if nobody would like to go outside with his or her estimation, so I would rephrase this very quickly. So if the size of the flat would increase by 1 square meter, so what would be the change? Here I would expect increase. So what would be the increase in prices of flat? So increase of the prices by 1 meter square increase in the sizes. In other words, I can say what is the average price of 1 square meter. It would be another interpretation. So these are only at the beginning only ideal, I would call it non-real interpretations, but in few minutes we will start computation, and of course we will start real case interpretations. So this is ordinary least squares and interpretation of intercept. Once again, quite often in social sciences useless, so that's why we will slightly shift this x-axis in my case, and this is interpretation of the slope, so it means influence of independent variable on dependent variable. Here on the next slide, it is only described by words, but I guess we can switch it as we covered this topic quite ideally. And here we will start computation. As we know from previous discussion and also from previous computation that we can somehow discuss about relationship by correlation coefficient. So this correlation coefficient is 0.685, and I guess that last time we discussed that this is quite strong or big correlation, which is positive. It means sizes are increasing, prices are increasing as well. So that's correlation coefficient. Now I will give you slightly different definition of correlation coefficient for regression. So I would move once again back into this picture, And as far as you know from your previous study, correlation for two variables means I will take values of the first one and second one variable, and I will input these values directly into the formula of correlation coefficient. So that's classical definition of correlation coefficient. For regression analysis, there is another option how we can compute correlation, and also there is another option how to interpret correlation. If I go back to previous picture, once again I can see that these points are quite far from this regression line. If I go to my real life example, these points are quite close to the line. And another alternative description of correlation in a regression is following. You can take the real values of my individual points. So here is the first size, second size, the third size, and the last one size of real point on y-axis. So I would take these sizes of dependent variable which are real. Then I can take these sizes for these red points. So it means for regression estimates. So this size, this one, and this one. And I can compute correlation for these real values of dependent variable and for these estimated values. And of course, you don't need to believe me. You can find mathematical proofs, maybe also on Wikipedia, I guess. But if I compute this correlation for these real values and estimated values, so this is the same correlation as correlation between independent and dependent variable. So this is how it works in regression. And it means that if these red points and these black points would be close to each other, it means if they would be the same, so all these black points would be here on the line, these sizes would be all the same and regression would be perfect, it means +1. If these points, real points, black points, would be quite outside of these red points on the line, correlation would be weak. So for example, here, this would be quite weak correlation, and for my data, it would be quite strong correlation. And in regression, not only computation of this correlation, but mostly we are computing the square from this regression, this correlation coefficient, and we call it usually coefficient of determination, or sometimes only R square. So here, for example, for this first case, this R square is, it is written here, is 0.33. For my case, I can compute it as the first time from my head. It is 0.7 approximately. If I make a square from 0.7, so it is approximately 0.49. So it is much bigger. So it means that these points are much closer to this regression line than for this picture, which was copied from Andy Field textbook. So that's only first introduction to the R square. And now we would ask for outputs for classical regression directly in JASP. So if I go back into regression, classical and linear regression, as we are using linear regression for these first cases. So I would ask for this dialog. I would need only to differentiate between dependent variable and so-called covariates. You can see, and this is quite newly designed in JASP, that for every variable window, there is some picture what is expected as the feature of the variable that would be included. It is quite strange that in some procedures, JASP will not allow you another variables that are not described here by pictures. For some procedures, it is still allowed, so it is not still fully predefined. But here we have continuous variables, so it is according to this predefined settings. So prices are dependent and sizes are independent. So once again, JASP is computing my results, and in a few seconds, I guess, we will get these results. And the first result we will be discussing would be this R. We know it is, for my case, 0.685 and R square, so we expect it will be slightly below 0.5. So we can go back and I can see my results. And the JASP is only automatically describing two models. One is usually called as H0 and one is called H1. So the model we have just prepared, so it means prices versus sizes, is H1. So every time the last one model is the model we expected to compute. The first one model automatically is the model in which there is no independent variable. It is usually called as constant only model, sometimes null model, sometimes empty model. And JASP automatically prepare this model for you as a comparative benchmark. But we will read only the second row, and here once again it is repeated that R, once again, for regression, it is correlation between real values and expected values by the model. And this R is 685. So this is the same value as previously. And if you make square, it is 0.470. And classical interpretation for this R square, it is also written here in the presentation, that you take multiplication by 100 and interpret in percentages as the percentage of explained variance. So the interpretation here would be, if I am discussing about explanation of prices by sizes of the flats, so it is influenced, so it means prices are influenced by sizes by 47%. 0.47 multiplied by 100 in percentages means that nearly 1/2 of variation of prices are explained by flat sizes. And now the question for you is, if you can help me to find another features that can explain prices of the flat instead of sizes. So some tips for other features that can explain the prices of the flats.
For instance, if is it new or old?
Okay, new or old. Other proposals?
The state. Okay.
Sorry?
Location.
Location?
Yes, I wanted to say the same.
Okay, some other proposals? For example, also the
equipment used for
equipment, whether it is somehow renewed or not, etc., etc. Okay, thanks all. We went into this discussion only to understand that in real life examples, especially for social sciences, this simple regression model is not enough. So it means there is usually more than one independent variable in reality, and we should include these in our model. But at least for this case, as we are trying to model prices of the flat by its sizes, so we were quite successful. By only one independent variable, we were able to cover, to explain nearly 1/2 of variance of prices. So that's quite successful case. That's also the reason why I decided to do this data. At least we should have success at first lectures. In next lectures, it will be much worse. This is quite successful case. Okay, so this is R square, and only you should be briefly informed that there are also some alternative formulas for this R square, for this measurement of explained variance, and these formulas are usually called as adjusted R square. why we should somehow adjust R squared. So there are at least two reasons, and I will mention only the one which is important for us. If you would add some other variables into a model, so it means whether it is new or not, whether it is in some big city or small village, etc., as we discussed previously, every time you include any variable in your regression model, this R square will be increasing, maybe slightly, but will be increasing. If you add even totally unuseful variable into our regression model, R square will increase. But this is quite bad property of some characteristic of the quality of the model. If you add some variable which is totally useless and your quality measurement says it seems better. So that's why statisticians develop approximately 10 formulas which are called adjusted R square, and they are based on R square, and they have also something what would be called penalty for difficulty. So it means if you add some more variables in the model, there is some penalty for this difficulty or complexity of the model, and model with more variables is somehow penalized. And if you like to compare models with different sets of independent variables, this adjusted R square should be used instead of original R squared. So this is the reason why we have two columns, R squared and adjusted R squared. Once again, adjusted can be used for comparison of more models with different number of independent variables. So that's R squared. Next table, which is called Anova Table, can be for this first introductory class of regression omitted. So there is no added value of this Anova Table if we have only one independent variable. So we wouldn't discuss about this table today. Next time we will cover this table and we will discuss what is the meaning of this test, which is called overall F test, which is included here. And now we would switch to the most important table. And if you are publishing results from regression, this is usually a classical table that is copied, and maybe R squared is added under this table as classical result in a regression. So here is classical table with coefficients. And once again, this is divided into two parts, H0 and H1. So for us, of course, the second part is important. And before we start to read results, once again, we would go back into our picture. And this table with coefficient is describing our parameters. It means, once again, B0 and B1. So it means what would be the price of the flat if the size of the flat would be 0 square meters, once again, quite useless, intercept or constant, and slope says what would be unit increase of the price of the flat. So here we have the values. So intercept or constant here is minus 29,000 approximately Czech crowns. So what would be the meaning? So it would mean that if I would buy the flat with 0 square meters, I would receive 29,000. I expect that everybody would buy such a flat. If somebody would give you money and you would take nothing for that, that's a great idea. But once again, real flats do not have 0 square meters. So that's why it's impossible to interpret this value. So we will try to somehow repair this problem in a few minutes. So the only value we can interpret is the coefficient for the size, which is approximately 14,300. And it would be nice if somebody can help me to interpret this value. So what can be the meaning of this value for size? Once again, it is this B1 or this B1 slope coefficient. So can somebody help me?
So this is the price for 1 square meter?
Yeah, it can be the interpretation, or maybe even more easier interpretation would be if the size of the flat is increasing by 1 square meter, the price is increasing by 14,300 Czech crowns. So these are interpretations. So if I go back to my previous picture, so it says that this line is going up for every 1 unit here by 14,300 here. So this is the expression for the slope. So this is the most important coefficient in my table currently. And before we start to discuss about other results that are included in this table, I would briefly go once again to the problem that I am not able to interpret realistically this intercept. So once again, classical case is that 0 on on x-axis means nothing. So there is no 0 square meters flat. For example, if you take age, there are no people, especially in classical social science research, that are just newborn babies, etc., etc. And that's why there is some option how we can change our case and how we can change the interpretation of this intercept. The easiest way is that we will somehow change this scale. So currently this scale is saying 0, 0 square meters, 1, 1 square meter, 2, 3, etc., etc. But another option is that if I go back to my picture, I can somehow change this 0 by shifting to the right. For example, I can take all these flats and I can try to compute the average for sizes of the flats. How to perform such an operation in JASP, it is quite easy. I would go into descriptives. JASP will open for me descriptive statistics window. I would take sizes, click on the right window, and JASP will compute for me that the average size of the flat, once again, we are excluding one extra big flat, is 64 square meters, 0.653. So this is the average. And I can take, once again, this picture, and I can take this point, which is the average, 64.653 square meters, and I can move this vertical axis to this average. So I would take this axis here, and 0 for this new axis would be the average size of the flat. And now, if I would take this new y-axis here, what would be the interpretation of the constant? Can somebody help me? So this would be intersection of this new y-axis and regression line. What would be the meaning of this intercept? So this size. It would be price of the flat for which the size is the average size. It means approximately 65 square meters. So it would be realistic estimate of the price for the flat with approximately 65 square meters. And we call this procedure, so it means this shifting of y-axis here in the center of my x variable as so-called centering. So now we would be performing centering of independent variable. And once again, why we are performing such procedure? We are centering this x variable to have an option to interpret constant. So if we would like to interpret constant, as for original variable 0 has no meaning, so we would shift this vertical variable here, and it would be possible to interpret constant or intercept. So it is how it works. and we need somehow to perform centering in JASP. So we need to take original variable size and subtract the value of the average 64.653 from every value. So for example, this first flat, 64 square meters in original, and for centered variable, it would be minus 0.5653, as it would be 64 minus 64.653. For the second flat, 50, the size would be minus 14.653, etc., etc. And now how it works, so you would go here into this black plus symbol on the right upper corner of data matrix. I guess we discussed about this option last time. You need to add some technical name. So if you are centering variables, it is usually quite useful to add some information about centering to original name. So if it is size, I would call this variable as C instead of centered size. So C size would be the new name. I would click here and here. So it means I would use JASP original computation procedure, and I would create scale variable and click into create column. And here is the dialog for computation of C size. We are computing something, that's why JASP is including here symbol fx, so it means it would be some function of previously defined variables. And I would take size minus, and now I would write 64.653. So I would subtract 64.653 square meters from every size to achieve a variable which would have new scale. 0 would mean average flat with 64.653 square meters. Below average would mean below 0, and above average would mean above 0 for the centered variable. So click into compute column, and now it is computed. We can check first two values, minus 0.653, correct, minus 14.653. So it seems it is correct computation. And now it would be the last one step, and then we will once again interpret results. So I would go once again into regression, into classical linear regression, and I would once again define the same dependent variable. It means price, but instead of size, I would take the last one variable which we have just created, which is centered variable for the size. So in a few seconds, JASP will recompute our results, and we can very quickly skip results from the first table, as the explanation must be the same. We have still the same variable, only we shifted the scale of independent variables. So explanation is approximately 47%. And what would be currently different from previous results would be the value of the intercept. Once again, here we were unable to interpret intercept. Here we are able to interpret intercept. It is nearly 900,000 Czech crowns, and it would be once again nice if somebody can help me interpret this value. So please, if somebody can help interpret, follow this interpretation. What is the meaning of this value nearly? Yeah.
It's a price for the average flat?
Yeah, it's estimation of the price for the flat with average size. Yeah, that's nice. And now it's possible to interpret intercept, so we are happy and we can follow this time. So only one short command. If you like to interpret your intercept, and 0 for independent variable has no meaning, so you must somehow rescale your independent variable. Of course, if you have more than one independent variables, you must rescale all these variables. So we will follow this discussion also next time in multiple regression. So this is the interpretation of intercept. The interpretation of C size is still the same, and the value for C size is still the same, as we only influenced intercept by centering. Only one more comment. We have just covered centering, which is called usually grand mean or global centering. So it means we were using as the mean which we were subtracting for every value of the size of the flats, which were total mean. Sometimes there are also some alternative techniques of something what is called group centering, but we will not cover this in this introductory course, as it is also usually related to some special regression techniques that are called multi-level or hierarchical regressions. So that's only for you to know that there is more than one possibility how we can center variable, and we have just applied some procedure that is called grand mean or global centering. Okay, so here is the first output and recomputation of constant, and last what should be discussed today is that we have just covered results that are descriptive. So it means for my data, so it means for this line starts currently for the new y-axis at approximately 900,000 and increase is per 1 unit of the size 4,300 Czech crowns. So that's a descriptive result. For my sample, it means for 262 flats in my data. But still, I would like maybe to somehow generalize my results from my sample to the population. And that's why JASP is offering some other outputs. Here, classically, some what is called t-tests. And we would add also some more outputs. So I would go into statistics and I would ask for confidence intervals at least. So here it is, statistics and confidence intervals. And JASP will add also confidence intervals here. And now we will cover these results that are included here. So it means results that can help me to generalize my results from the sample to the whole population. So if we have here some sample of flats from some Czech region, so we can generalize to the whole region from which these flats were selected. So first of all, and classical tool for generalization in regression is called usually partial t-test. So here is the t-value, and this t-test is based on following logic. You would test whether this variable, it means size of the flat, is influencing prices of the flats. So null hypothesis will inform you there is no relationship between sizes and prices, once again, for the whole population. It means for the whole region from which we sampled my data. So null hypothesis would tell me there is no relationship. An alternative, it's quite easy to guess, is there is some relationship. It means that here the coefficient for my sample is 14,300, and it wouldn't be 0 also for the whole population. And if we know about hypothesis, so now only brief insight how it works. So you take the value of the coefficient itself and you divide it by something what is called standard error. If you do not remember what is standard error, I would propose you can go back in your previous statistical lectures and you can repeat this concept of standard error. So you take the value, divide by standard error, and this ratio is following approximately t-distribution, which is very close to normal distribution, only t-distribution has longer tails than normal distribution. And if your sample size is more than 30, so t-distribution is nearly the same as normal distribution. So here the ratio of these two values is approximately 15. I guess that you know from previous discussion about standardized normal distribution that the values outside of the range, -2 and +2, are quite extraordinary. Only 5% of all values, standardized normally distributed variables, are outside of this range. So 15 is extremely big value. And once again, we can use directly this t-value, or we can use p-value for the evaluation of the test. So for t-value, the decision would be made. If t-value is outside of the range -2 +2, I would reject null hypothesis and I would accept alternative 1. So it means I would say, it seems that also in the whole population, size is influencing the price of the flat. Another alternative option is choose p-value, so to forget about t and borders such as -2 and +2. And for p-value, I need, before I start, set up somehow alpha level, which is maximum accepted risk for rejection of null hypothesis, which wouldn't be correct. Once again, in social sciences, we are usually following 0.05. It means 5%. Current recommendation in the literature discussing lower limits such as 0.01 or 0.005. But nevertheless, here we have very small value, 1.112, and exponentiated -37 means that this value is 0.then 36 times zeros after decimal place, and then 1. So it is very small p-value. So if we compare this very small p-value with some previously defined alpha value at 5%, 1%, or even 0.5%, so it is still very small one. So p-value is very, very low. So once again, we would reject null hypothesis and say, okay, it seems that sizes are somehow influencing prices. But if we sum up all these procedures, so here the coefficient is 14,300. We have quite medium sample size, 262 flights. So we were not expecting that we wouldn't say, okay, there is some relationship between sizes and prices. We also know from previous discussion about correlation that this correlation is very, very strong. So maybe that this testing of zero coefficient is quite useless. But of course, it's up to you to decide whether to use this procedure or not. It is quite classical procedure in regression analysis. Maybe more useful is the next approach for generalization of my result, which is confidence interval, by default 95%. But if you like, you can change these settings in this confidence interval window. But what is the meaning of this 95% confidence interval? The real value for my sample is 14,300. The real value of the estimation of so-called sampling error by standard error is 941. And classical formula for confidence interval is that you take your real value for the sample and you take 2 times plus and 2 times minus standard error, and you would take 95% confidence interval. So this value plus minus 2 times 942 would give me such results. And this is the rough estimate what can be the regression coefficient for the whole population. So here I have 260 flats, and I would like to generalize to some maybe thousands or 10,000, 100,000 of all flats in this region. So I expect that the regression coefficient for all flats would be somewhere between 12,500 approximately and 16,100. So that's my expectation about real value of regression coefficient for the whole population. And maybe that this confidence interval is more useful than this testing. By testing, we only can recognize whether there is some impact or not. But by confidence interval, we can somehow recognize what would be the impact of independent variable on dependent variable. And here we can see that original value for sample is maybe slightly lower or slightly higher in the population, but it is still quite substantive relationship. Maybe this is also why in current literature you can find a recommendation that if you are computing some quantitative results and if you are trying to generalize your results, maybe instead of testing or together with testing, you should also apply confidence interval and you should interpret these upper and lower bound of this confidence interval. So that's about t-test and about confidence interval in regression analysis. Of course, you can also use this confidence interval for Intercept. So as we previously discussed, that the price for the average flat was approximately 900,000 Czech crowns. So according to this confidence interval, we can expect it could be maybe 860,000 Czech crowns, or it can be also as high as 930,000 Czech crowns. So this is confidence interval for constant that can be also useful to interpret. Last one, result, but we will discuss about it in detail next time, is a standardized coefficient. If you have only one independent variable.
Excuse me?
Yeah?
Can I ask? You have very specific p-values, and in my JASP, I have very simplified.
Yeah, I will show you how to change it. Yeah.
Yes.
Thanks a lot.
Thank you.
Maybe this is not the default. So you have some rounded format and I have some precise format. So if you like to change it, you can go into these 3 blue lines. So it means into settings. Then you can go down into preferences, and here 2 results. And here you should check option which is called display exact p-values.
Thank you.
By this change, your results should be shifted to these precise p-values. Currently, once again, in the literature, it is recommended that we should interpret and publish the precise p-values. That's why these are settings in JASP. Okay.
Okay, thank you so much.
Thanks for the question. I hope it works. So that's all for today about regression. But once again, I would go back into the standardized coefficient. We will discuss about the meaning next time. But currently, if we have only one independent variable, you can see that this standardized coefficient is the same as correlation from the beginning. So for one variable only, the standardized coefficient is nothing more than correlation coefficient. So that's all for today from my side. Of course,